Hi everybody! In this video, we will be talking about NP completeness and NP reductions. We have already talked about time classes. For instance, the P class or polynomial time class is algorithms that take some sort of polynomial time to run. An example of a problem in P is path. There's also the concept of NP, where it takes non-deterministic polynomial time to run. We can talk about P versus NP as well, saying that a problem that's in P is polynomial time to solve, whereas a problem in NP is polynomial time to verify. Let's go ahead and start looking at the material. The definition of the time class is that some deterministic one-type Turing machine decides this particular problem. The input to the time class is the set of problems, or you can think of it as languages, but this Turing machine M, it exists and it decides B in this time T of n. When we talk about polynomial time decidable languages, we say that it runs in time n to the k, where k is some constant. N is going to be the size of my input. One example of a p-time algorithm is path. Path is going to take in input g, st, where g is a graph and s and t are nodes in that graph. We claim that path takes polynomial time. Another problem that also takes in GST is Hamiltonian path, or short Ham path, where we say G is a directed graph with a path from S to T, where this path goes through every node of G. The question is then, is Ham path in P? It's actually an unsolved problem. We can do it in NP time, but it's unknown whether it will be in polynomial time or in P. In a non-deterministic Turing machine decider, all branches halt on all inputs. The definition of n time is going to be the set B of problems where some one-tape non-deterministic Turing machine decides B and runs in time O of T of n. We are starting to think of B as a problem, so we want to provide a solution to an instance of a problem in time O of T of n. Previously, we were thinking of B as strings, and now we're starting to think about problems and algorithms, so we are starting to take those problems, converting them into strings, and making that connection between languages and problems or algorithms, which are probably a little bit more natural to think about. Now, an NTM runs in time T of n if all branches halt within T of n steps. That creates this computation tree. Thinking about this computation tree, you have an input W, and you guess what is the next best step when I am trying to solve this problem. Should I pick this answer or this answer? And eventually, if you follow a branch all the way down, that will be a certain set of steps that you have picked that will represent an answer to the problem. As long as all branches halt within T of n steps, then that Turing machine is considered a run in time O of T of n. It's in n time T of n. Non-deterministic polynomial time, or for short NP, is the set of all languages that run in non-deterministic polynomial time. In other words, n time of n to the k, where n is the length of the input and k is some constant polynomial. It is invariant for all reasonable non-deterministic models. That means, going back to the Church-Turing thesis, that it doesn't matter if I had 1 tape, 2 tapes, or another model of computation, it's still going to run in polynomial time. You can get a polynomial time speed up, maybe. Perhaps you go from n squared down to just n, but it's still going to be polynomial time. We don't get a win faster than that as long as it's a pretty normal sort of model. NP is also going to correspond roughly to easily verifiable problems, which I'll talk about a little bit more as we move forward. Let's talk about ham path. Ham path is in NP. Remember that the input of ham path is going to be a graph and a start node and an end node, S and T. We're going to say that we want a sequence of the nodes, so V1 through Vm, where V1 is the start node and Vm is the target or end node. And we also have to make sure that there is an edge between each of the vertices in our list and that none of them repeat. If that's not true, we will reject. Thinking about this, we wanted to find a path that went from a start node to an end node, and it went through all of the other vertices or nodes in that graph. Thinking about the computation tree, we're basically guessing what that first vertex is, and then the second vertex, and then so on until we get to the last one. To actually verify this computation, you just take that list, V1 through Vm, and make sure that it's correct. Thinking about the number of possibilities that the path can have, we have m nodes, therefore m factorial different orderings of those nodes. But there is only one, perhaps more than one solution that is of length m, and verifying that solution will take time m. Since verification is only going to take time m, whereas actually computing the Hamiltonian path would take more like time m factorial, this shows us that it's easy to verify. If I give you the answer, you can check it pretty quickly. It's not so easy to solve as far as we know, but it is easy to verify. Another interesting problem is composites. Thinking about composites, those are numbers that are not prime, and that means that that number has a factor. So x is going to be equal to y times z, where y and z are both greater than 1. Composites is in NP. Thinking about being able to easily verify it, if I want to give you a proof that composites is in NP and you wanted to verify it, you take that input x and then I give you y. If y divides x, you would have to run a division algorithm, which takes polynomial time. Then you'll accept. Otherwise, you reject. The way that it's written on the slides, it says we're guessing, non-deterministically right, y. You can also think of it as someone has given you the solution. It does not matter if I'm in binary or base 10, because you can convert in polynomial time between bases. The exception to that rule is that if you wrote your number in unary, then that number is exponentially longer. While log 10 and log 2 are related to each other by a polynomial, there's not a concept of log base 1 since it's literally just tallies. And so that is the one exception to the rule here about what the length of that input is. It does turn out that composites is in P, meaning that you can even solve it in polynomial time. That proof comes from 2002. We're not going to cover it. However, I do want you to be aware that composites is in P. The definition or intuition for NP is languages where you can verify membership quickly, whereas P is languages where you can test or perhaps solve for membership quickly. Examples of quickly verifying membership are HamPath, you just give the Hamiltonian path. Composites, you give a factor. The Hamiltonian path and the factor are called short certificates of membership. You might also call them a short proof or a short witness. Because you can test membership quickly in P, meaning that you could actually solve the problem pretty quickly and determine for yourself if the answer is correct, it is clear that P is a subset of NP, where NP is only if I give you the solution, you can check it quickly. It's unclear, though, whether there's actually a faster way to do HamPath, a better algorithm that we just haven't solved yet. And so that is the great question of computer science, which is, does P equal to NP? Most people believe that P is not equal to NP, but there is no true proof that has, as of November 2025, come out. Some problems are in NP and not in P. That's what it would mean for P not to be equal to NP. It turns out polynomial time algorithms are pretty powerful. Thinking about n to the k, if you have k, it can be a really bad polynomial, n to the 1,000, n to the 1 million, and it would still be polynomial time. Thinking about how big that class is, it is unclear simply to prove that polynomial time algorithms couldn't solve these problems in NP. We are going to look at this idea of a CFG being in P in a little bit. First, let's talk about not HamPath. Not HamPath is the complement of HamPath. Recall that when I give you G, S, and T, and then I give you a path, V1 through Vm, you can check it. GST is an instance where that graph does not have a Hamiltonian path. It does not matter what sequence of nodes I give you, none of them are going to be a Hamiltonian path. And the question becomes, is not HamPath in NP? Thinking back to that computation tree, looking at the first answer choice, it says, yes, we can invert the accept-reject output of the NTM for HamPath. This answer is false because thinking about those branches, all of them are many of them are going to be no, some of them are going to be yes. If you want to check that it's no, you actually have to check all of the different branches to be clear. I have to give you every sequence of M nodes and you have to check all of them and be convinced that all of them are no. So you don't really get to save any time that way. So that leads us into question or answer choice 2, which is no, we cannot give a short certificate. I just argued about why it was not possible to give a short certificate. So this answer choice seems valid until we remind ourselves that we don't actually know whether P is equal to NP. Given that, the answer choice C makes a lot more sense. I don't have, that I know of, a short certificate for not HamPath, but if it did turn out that P was equal to NP, then you would be able to invert the certificates very quickly. You would be able to get an answer, because if I can get a yes answer for HamPath very quickly, it also means I could get a no answer for HamPath very quickly. So really, the best answer choice is C, I don't know, for the reason given by B, which is we don't know if there's a way to give a short certificate of a graph to not have a Hamiltonian path. HamPath is in NP, which we said earlier. Not HamPath is going to be in this language called co-NP. Co-NP meaning the complement of languages that are in NP. One of my favorite languages to go back to thinking about being a decider, and then also reminding ourselves when we talk about Turing machines, we think about strings, is ACFG. ACFG is the language of grammars and words together. G is a CFG, and we want to say, is W in that language given by that grammar G? ACFG is decidable. We've seen this in some other videos or in lecture where we put an algorithm to show why it is possible to decide it. You just run all of the different derivations that could possibly output W, and if any of them are good, then you accept, and if all of them are bad, then you reject. It turns out that you can always, for a string of W, find out whether W is in that language. The derivation would be at most length 2 times length of W minus 1. Given that, we know that's decidable, which is good, and then that allows us to say ACFG, can we check if it's NP? We just need to say, is there a certificate that can be checked in polynomial time? Looking above, we said we wanted to try all derivations. So what we would say is, let's pick a derivation, and if that derivation is good, then it means that we would accept. So you can verify that derivation. That derivation is of length at most 2 times length of W minus 1, which is polynomial time in the length of the input. There is a concept known as dynamic programming, which uses memory to store subproblems, and if you use dynamic programming, you can use that to prove that ACFG is actually in P. However, dynamic programming is not within the scope of this class, and so I'm just going to leave the slide here for those of you who are interested, and we'll move on to the next set of material. Let's move on to talk about the satisfiability problem, which is the canonical NP problem. A Boolean formula has Boolean variables, which are true or false, and Boolean operations, and, or, and not. A formula phi is satisfiable if phi evaluates to true for some assignment to its variables. We often use 1 for true and 0 for false. So for example, let's say phi is equal to x or y in parentheses and not x or not y. Then phi is satisfiable. I can tell you that if I assign x to be true and y to be false, then this will work out. This is not the only satisfying assignment, but it is one of them. The language SAT is the language of formulas where phi is satisfiable. This is the canonical NP problem because in 1971, Cook and Levin proved that SAT being in P would imply that P is equal to NP. And we'll talk about this in a moment, but we are going to see that there's a polynomial time mapping reduction from all problems in NP to SAT. With that, I give you this question. Is SAT in NP? Yes? No? I don't know? No one knows. Well, I just said SAT is a canonical NP problem, so that helps. I also told you that all problems in NP reduce to SAT, so the answer is yes. The open question is whether SAT is in P. That is not something that we know. Now, going back to the definition of NP, the definition of NP says if I can verify in polynomial time, then it's in NP. If I give you a formula and then I say, here is how I assign my variables, x, y, and so on, I could have n variables, you just plug them in and then check if the whole thing evaluates to true. And you can see then that the time to verify is polynomial. Now, in terms of the number of assignments that there are, with n variables, there are 2 to the n many assignments. So it's not very clear. Nobody knows if there's a way to find that assignment in polynomial time, given that the space is so large, but SAT is definitely in NP. Given 2 languages, A and B, or problems A and B, A is said to be polynomial time reducible to B if A mapping reduces to B, and that mapping is computable in polynomial time. That mapping is called a reduction function. So thinking back to mapping reductions, if I have an instance of a string that's in A, then f of that instance is going to map it to something that's in B. If that instance is not in A, then f is going to map it to something that's not in B. In other words, yes goes to yes and no goes to no. The main theorem here is that if A polytime reduces to B and B is in P, then A is in P. Thinking about that, if I give you a question that's in A and then you compute F, you go to B, you solve for B, and then since you know yes in B means yes in A, you already have your answer for A, and then of course no in B means no in A. Looking back at the Cook-Levin theorem, SAT is a problem that's in NP. Cook and Levin proved that all problems in NP polytime reduce to SAT. This might feel a little analogous to when we talked about decidable languages and recognizable languages, and we saw that ATM, the acceptance language for Turing machines, is recognizable but not decidable. And you can mapping reduce languages that are recognizable to ATM. Just to put things together, remember A is polynomial time reducible to B if A mapping reduces to B by a reduction function that is computable in polynomial time. And if A polytime reduces to B and B is in P, then A is in P. NP is all languages where you can verify membership quickly, and P is all languages where you can test membership quickly. The P versus NP question is whether P equals NP. And then we talked about SAT, which is the language of satisfiable Boolean formulas. The Cook-Levin theorem says SAT is in P implies that P is equal to NP. The idea for the proof is that you would show that every A in NP is polynomial time reducible to SAT. To conclude this part of the video, we've talked about N time, NP. We described ham path and composites as examples of languages that are in NP. We talked about the P versus NP question. We discussed that ACFG was an NP. We talked about the satisfiability problem and that it was an NP. And we talked about polynomial time reducibility. So again, N time, NP, P versus NP, ACFG is an NP, and polynomial time reducibility. With these concepts in mind, we can now start talking about NP completeness. NP completeness. B is NP complete if B is an NP, and for all A and NP, A polytime reduces to B. If B is NP complete and B is in P, then P is equal to NP. Thinking about SAT, SAT is NP complete. There's a special type of reduction where all problems in NP were shown to reduce down to SAT. This is too much for the class, so it's skipped, but we will take it for granted because now that we know all problems reduce down to SAT, we can use that to make further reductions. SAT reduces down to 3 SAT, which reduces down to clique, which reduces down to ham path. If you wanted to show that a particular language is NP complete, a good way to do it is to pick one of the ones you already know, like 3 SAT, and then reduce it down to that language. Now, we're going to talk about a particular example where I show some language and I show how to do a reduction between the two of them. And that will show you that that particular language is going to be NP complete. As always, the thing that you need to take away from this class is definitions are important, so remembering that the definition of NP complete requires two parts. B is an NP, and for all A and NP, A polytime reduces to B. And so for part B, when you say for all A and NP, A polytime reduces to B, if I use a language that I already know that all NP languages reduce down to that, I can use that for my further reduction. The importance of NP completeness is showing that a particular language is NP complete is evidence that it's probably hard, mostly because we believe that P is not equal to NP, even though nobody really knows that that's true. It's another candidate for proving that P is not equal to NP. So if you have a problem that's NP complete and you show that it is absolutely not in P, then you would be able to prove that P is not equal to NP, which people do. They'll take some problem like Sudoku, which is NP complete, and they'll try to show that it is not in P. None of these proofs have worked out, but you can really pick anything you want and go from there. So the question I have for you is, what language have we seen previously that is most analogous to SAT? A, ATM, which is the acceptance language for Turing machines, ETM, which is the empty language for Turing machines, and then C, 0 to the k, 1 to the k, k greater than or equal to 0. And going back to recognizable languages, we saw that with ATM, we were doing mapping reductions down to ATM for recognizability, and so we proved ATM was undecidable by using diagonalization. And from then on, to show other languages were undecidable, we used ATM, and so that's where that analogy comes from. The particular example that I'm going to show you is that 3SAT and clique have a reduction. I have to explain, of course, what these problems are. 3SAT, we talked about SAT, that has a Boolean formula. Now, 3SAT is going to be a formula that is in conjunctive normal form. A formula phi is in conjunctive normal form if it is ors separated by ands. So for example, phi is equal to x or, not y or z, that's together, separated by an and to another clause, not x or not s, or etc. The individual letters or the not of them are called literals, and then the things that are separated by the ors, the literals separated by the ors, are called clauses. And then we and together those clauses. So a literal is a variable or a negated variable. A clause is an or of literals. A CNF, or conjunctive normal form, is the and of those clauses. A 3CNF is a CNF with exactly 3 literals in each clause. And so looking at the example I have here, I have x or not y or z, which is 3 literals. So that would be so far in 3CNF, form. But then I go to this next clause, which is not x or not s or z or u, which has 4 things in it, and that kicks it out of 3CNF. 3SAT is the language phi, where phi is written in that 3CNF format, and phi is satisfiable. The other language I need to define is clique, which is a graph problem. A k-clique in a graph is a subset of k nodes all directly connected by edges. In other words, it is a subgraph that is a complete graph on k nodes. Some examples include the 3-clique, which is a triangle. The 4-clique, you have 4 nodes and they're all attached to each other. You can have a 5-clique, and so on and so forth. Clique is the language of G and K, where G is a graph and it contains a k-clique. We are going to show that 3SAT reduces to clique. 3SAT reduces in polytime to clique. Proof. Give a polynomial time reduction f that maps phi to gk, where phi is satisfiable if and only if g has a k-clique. Remembering that IFF, if and only if, it's a biconditional. because we want F to map yes to yes and no to no. So we have to make sure that it preserves that membership. And many of the proofs that we do in this class are by construction. To prove that 3-sat polytime reduces to clique, we have to give that construction. And that construction is literally the function that we're going to describe. Let's work through this. I will give a phi in 3CNF format to demonstrate it as an example. And so phi here is A or B or not C, and not A or B or D, and A or C or not E, and blah, not X or Y or not Z. Taking a look at this, since we have ors in each clause, we just need to have one true literal. We can have more than one, but we just need at least one. Then looking at phi, we want to somehow turn something that is a Boolean formula into a graph, which might seem unusual because the problem domain is very different. But remember, everything is strings and everything can be encoded in one way or another. Thinking about G, I can take those literals and I can turn them into nodes. So A or B or not C gives me the nodes A, B, and not C. That's how they are labeled. It's a graph, so I need to think about edges. Well, I'll talk first about forbidden edges. There are going to be no edges within a clause. And I am not going to be able to have inconsistent labels. So there's no edges between A and not A. G is going to be the graph that has all non-forbidden edges. K, what is that? Thinking about 3-sat, it's 3 things in an OR ANDed together. K is going to be my number of clauses. Looking at the graph G, if I am looking for a K clique and there's K clauses in phi from where I started, I really just want one of those nodes to be true, and that will be the node that I'm going to include in my K clique. So the claim is phi is satisfiable if and only if G has a K clique. Since this is a biconditional if and only if, we have to do the forward direction and the backwards direction. The forwards direction is take any satisfying assignment to phi. That's going to be the true literal in each clause. So if A is true, I'm going to pick that node in G. If C is false, I would pick that node, not C. The corresponding nodes in G are going to be a K clique. So all the trues that I pick are going to form a K clique because they all had edges between them. In the backwards direction, if I take a K clique in G, then it has to have one node in each clause. I'm going to set each of those nodes to be the trues in the literal. That will be a satisfying assignment to phi. By the way, this kind of construction, it's called a gadget. It's not so easy to come up with. Of course, it feels a little bit easy when I tell you these things, but somebody already solved this. Finding these reductions is a particular art of trying to map problems to one another. So actually watching this video a couple of times to make sure you understand the construction, but also knowing that if I wanted to solve a problem of doing this polynomial time reduction, it might be hours, weeks, or even years of work, and some things are still not shown. It's okay that this is a little bit tricky. Lastly, we just want to make sure that we understand that that reduction f is computable in polynomial time. And just saying that we had n nodes that were mapped to by n literals, over k clauses, you can see that it's going to be polynomial time overall. Of course, the corollary here is that clique is in P would imply that 3-sat is in P. If I told you that I already knew a reduction from sat to 3-sat and from 3-sat to clique, then I can say clique is in P implies 3 sat is in P. So going back to my order, I had all problems in NP down to sat, down to 3 sat, which then goes to clique. That is telling me that clique is actually NP complete. HAMPath is NP complete. Next, we're going to show that 3 sat polytime reduces to HAMPath. So we already believe that 3 sat is NP complete. I skipped the one from sat to 3 sat, but it's all good. And I mentioned before that we're going to simulate variables and clauses with this idea of gadgets. I'm going to go a little bit fast, but the idea is that I have my 3CNF formula, and then I'm going to map it down to G. And thinking about my literals, those literals are now forming these kinds of subgraphs where I have x1 along this edge and s, and that's going to cause us to create this thing called a variable gadget. And there's going to be some sort of path that we create through it. If we do a zigzag, it corresponds to setting x1 true, and a zag-zig corresponds to setting x1 false. And then you set it to this thing called a clause gadget. So part of the reason of showing this is the one from 3sat and clique, the mapping is just node to variable, or variable to node, whereas with HAMPath, this mapping takes nodes and it creates a particular kind of graph with a path. And really the goal here is to show you can do a little bit more, and it can be a little bit complicated to create this type of reduction function. So just thinking about this construction, we have clauses, we create these fancy gadgets, we connect them to these clause gadgets, which are nodes, and then thinking about whether it's going to be a true literal or a false literal, whether it's negated. Again, I don't really expect you to know all the details here, just that there is a reduction and it uses this concept of a gadget. Now, the claim, of course, is that phi is satisfiable if and only if G has a Hamilton path from S to T. We're going to take any satisfying assignment to phi. We'll make corresponding zigzags and zag-zigs, and we'll make detours to visit the clause nodes, and that will be a showing that satisfiability implies that G has a Hamilton path. On the other direction, if I have a Hamiltonian path from S to T, it's going to correspond to zigzags and zag-zigs with detours to visit all CI. You do not need to know this proof. You just need to know that Hamiltonian path is NP complete and that we can make a reduction using 3sat. Something that, if you're interested, you might like to think about, can we rewrite this question to be a construction where we made G undirected, and can we show that the undirected Hamiltonian path is NP complete? And the answer is yes, the construction would still work, or no, the construction depends on G being directed. So you're welcome to think about that. Leaving off here at the end of the video, I want to give some examples of problems that we might see on an exam or maybe a homework, which is showing that certain things are in NP or in P. Thinking about whether things are in NP, you usually just want to show that you can verify it in polynomial time. If you want to show that something is in P, you would have to show an algorithm that can run and actually solve the problem in polynomial time. So some example problems that I like is the concept of unary versus binary. So looking at problem 2 here, unary S-sum is just some problem where the numbers are represented in unary. And thinking about the fact that the number k is k ones in a row, that indicates that the length of my input is already kind of exponential. So when I run the algorithm, it's only going to be poly in k. So things in unary often run in polynomial time, but it's an encoding that doesn't work for any other base. If I wrote my input in binary, I have log base 2 of the length of the input of the numbers, meaning that input is log, which means if my runtime is in n, then it's going to be exponential if that is my algorithm. So that is an important concept. There's going to be a couple of questions where you can say, if p was an np, then we could do this particular thing. So for question 3, you say, if p is equal to np, every language is in p except a is the empty set and a is sigma star is np complete. You can also show particular questions. If p is equal to np, then we can factor integers in polynomial time, because that's a problem that we know is in np. And so you can say something like that. Okay, so those are just some example problems that I recommend working through in your own time. Okay, just to complete this video, in conclusion, we've talked about NP completeness, we talked about SAT and 3-SAT. We showed 3-SAT reduces to hand path, we showed 3-SAT reduces to clique, and the overall strategy for proving NP completeness. Normally we reduce from 3-SAT by constructing gadgets that simulate variables and clauses. And overall, a strategy for NP completeness is reducing from a problem that you already know is NP complete. You are always welcome to use any problem that is already known to be NP complete to do your next reduction if you are asked to do so. That's it. Thank you for watching.